All right, let's talk about choosing a fuse. How hard can that be, right? Well, what if that fuse is the only thing standing between a 40-ton hybrid cement mixer and a catastrophic failure? Yeah, suddenly simple isn't the word you'd use. Today, we're going to dive deep and decode the massive challenge of protecting one of the toughest high-voltage systems you'll ever find on wheels. Okay, so take a look at this. This is basically the entire playbook for protecting that cement mixer, all on one page. And I know what you're thinking. It looks intense. But stick with me. We're going to break this whole thing down. In the next few minutes, every piece of this puzzle, from the math behind it to something called the forbidden zone, yeah, that's a thing, it's all going to click into place, I promise. So how are we going to tackle this beast? We're going to do it like a top-tier consultancy would. We've broken it down into 6 logical steps. First, we'll get a handle on the problem itself. Then, we'll lay out our strategy. After that, we'll crunch the numbers, tackle a huge safety gap, prove our solution works in the real world, and then at the very end, boil it all down to 3 simple rules you can take with you.
Okay, first things first. We've got to understand why a cement mixer isn't just a big car. It's a completely different animal. The demands on this thing are so extreme that if you just grab a standard automotive fuse off the shelf, well, you're not just making a mistake. You're creating a serious hazard. Let's dig into the 3 big reasons why.
So, challenge number 1, the inrush current. Just picture it. You've got that huge drum full of tons of concrete that's starting to set. Getting that thing to spin again after it's been sitting still, that's not just a startup. It's like trying to break a motor free from a stall on purpose. The surge of electricity needed is just astronomical, way beyond anything a regular electric car would ever experience.
Next up, we have something called thermal fatigue, and it's brutal. Think about the fuse's tiny metal wire. Every single time the truck speeds up, it gets hot. Every time it brakes and regenerates power, it cools down. Now imagine doing that over and over and over again for 1,000,000 kilometers. It's like bending a paperclip back and forth. Eventually, that metal gets tired, it develops tiny cracks, and it's going to break. And you can bet it'll happen at the worst possible moment. And last but not least, the environment itself is just an absolute nightmare for electronics. I mean, we're talking about a construction site, right? So you've got blistering heat, non-stop vibration that rattles your teeth, and maybe the worst part, fine conductive cement dust that works its way into everything. Each one of these things on its own is an attack on your system's reliability. Put them all together, it's an all-out war.
Okay, so with challenges like that, how on earth do you design something that's going to last? The answer isn't a bigger fuse. It's a smarter strategy. We call it the protection pyramid, and it requires a total shift in how you think about fuses. Here's the key. The fuse isn't your first line of defense. It's your absolute last resort, the final backstop.
So here's how this layered defense actually works in practice. Layer 1. The first responder is the software. In milliseconds, the battery management system, the BMS, can see an overload coming and dial back the torque. It's the quick, intelligent fix. Now, if the problem's bigger than that, we go to layer 2, the contactor. Think of it as a giant, heavy-duty light switch that can physically cut the power for a more serious fault. And only if something truly catastrophic happens, like a massive short circuit that blows past the first 2 layers, does the fuse step in and make the ultimate sacrifice. And this right here. This is probably the single most important takeaway of this whole thing. I want you to burn this into your brain. A fuse is not an overload protector. It's not. It's a one-shot, break glass in case of emergency device for complete disasters. If you're designing your system to pop fuses during predictable high loads, you're doing it wrong, period.
All right, so we've got our strategy. But strategy is one thing, math is another. How do we take all those real-world problems, the heat, the shaking, the fatigue, and actually turn them into a concrete number? A fuse rating we can actually spec? Well, that's where we introduce what I like to call the golden formula. Now, take a look at this formula. It might look a little intimidating, but the core idea is simple. The actual current the motor uses, that's just the beginning of the story. The real engineering, the smart part, is dividing that number by all these other factors, these derating factors that account for all the real-world punishment the fuse is going to take. That's how we get from a basic number to a truly reliable one.
Let's zoom in on the 3 big ones for our cement mixer. You've got KE for temperature, that handles the crazy heat inside the power distribution unit. Then there's KE for connectivity, which accounts for those intense vibrations.
But the real game changer, the one that truly separates a passenger car from a heavy-duty commercial beast like this, is KC, the cyclic load factor. This is the magic number that accounts for the metal getting tired after 1,000,000 kilometers of starting and stopping.
Okay, let's put some real numbers to this. The motor on our cement mixer draws a steady 300 amps of current while it's working. Simple enough, right? If you were in a perfect lab environment, that might be all you need to know.
But we are so far from a perfect lab environment. So after we run that 300 amps through our golden formula, after we account for the heat, the vibration, and especially that decade-long fatigue, what number do we get? Not 300, not 400. We get 635 amps. Think about that. We need a fuse rated for more than double the actual working current. And that right there is the key insight. To build something that lasts, you have to be aggressively, almost ridiculously conservative. So, you've done the math, you've picked your super conservative fuse, you're safe, right? Well, not so fast. There's a dangerous blind spot in these high-power systems, a gap in your protection that's often overlooked, where things can go horribly wrong. Welcome to the forbidden zone. So what is this forbidden zone? It's a nasty little gap between your second and third layers of protection. Imagine a fault current that's too powerful for the contactor to handle safely, but not quite powerful enough to make your big, slow-melting fuse blow quickly. What happens? The contactor tries to open the circuit, gets overwhelmed, and can literally weld itself shut or even explode. And all the while, your fuse is just sitting there getting warm, completely unaware of the disaster that's unfolding. It's a recipe for catastrophic failure. So how do you get out of this terrifying no man's land? The solution is really cool, actually. It's a piece of tech called a pyrotechnic fuse or Pyro Fuse. See, a normal fuse waits around to get hot enough to melt. A Pyro Fuse doesn't wait. It gets a direct electronic signal from the system's brain, the BMS, and it triggers a tiny, controlled explosive charge. The reaction isn't slow, it's basically instant. We're talking under 2 milliseconds. It doesn't just make the forbidden zone smaller, it completely erases it from existence.
Okay, the strategy is sound. The math checks out. We've even got our fancy Pyro Fuse to close the safety gap. But that's all just on paper, right? None of it means a thing until you can prove it. You have to prove it can take a beating in the real world. So now we move from the whiteboard to the test lab.
And a proper verification plan for something like this has to be brutal. You have to simulate the worst day on the job. That means baking the fuse at max load on a hot day. It means hitting it with a full-blown 20,000 amp short circuit to see if it holds. It means running it through 50,000 plus on-off cycles to simulate its entire life. But the absolute king of all tests, the one you cannot skip, is the commercial vehicle vibration test, ISO 16753. If your component can't survive being shaken that violently, it has no business being on a truck. End of story.
So we've been through a lot here. The challenges, the strategy, the math, the tech, the testing. After all of that, we can distill this entire playbook down to 3 core principles. 3 simple rules to live by if you want to build a truly reliable high-voltage system.
All right, here they are, the 3 big takeaways. Number 1, be aggressively conservative. Don't design for today, design for 10 years from now. That means using extreme derating, especially for fatigue. Number 2, demand commercial-grade proof. Don't let anyone tell you that a passenger car standard is good enough. It's not. Mandate the proper vibration tests. And number 3, embrace hybrid protection. Use smart tech, like a Pyro Fuse talking to the BMS, to engineer away the dangerous blind spots that old technology leaves behind.
Think about it. We just spent all this time on a fuse, a component most people don't even think about. It really shows that as we electrify everything, there are no simple parts anymore. Everything is part of a complex system. So it leaves you with a question, doesn't it? As we push electrification into bigger and tougher machines, what's the next supposedly simple component that's going to need its own systems engineering playbook?